Welcome back to statistical analysis. Let's look at an example. You hypothesize that the IQ of the Hopkins Carey business student is 112. You randomly select a sample of 81 students and calculate the IQ score, average, to be 118. We're going to test the hypothesis using a significance of 0.05 and a population standard deviation of 15. First step, let's list the values with the correct mathematical symbols. So we said that the population standard deviation sigma is 15. N is equal to 81, and x bar, our sample mean, is 118. Now we indicate in the words that the Carey Business School student's IQ is 112. So we have no words that indicate an inequality. So therefore it's equal. Null hypothesis, mu equal to 112. Then the alternative is mu not equal to 112. Let's do our diagram, and we'll indicate that the rejection areas are determined by our alpha value, 0.05. Since it's an equality, it is a two-tailed test, and we split that significance between the two tails. So we have 0.025 area in each of the tails. Next, we will do our calculation to determine the values that define that do not reject area. That's our hypothesized mean plus or minus z times sigma divided by our square root of n. So now let's plug in those values, and our z value here is 1.96 because again we have the area in here of 95. We divide 95 in half to give us a value of 0.4750. So our z value is 1.9. When we go to the top, we'll see that's 1.96. Okay, so we do that calculation, and our critical values are 1.08, 0.73, and 115.27. Now we look at where does our sample mean fall. Well, the 118 falls in that right tail in the rejection region. So now we conclude that we will reject the null. The student's IQ do not equal 112. It is significantly different. Now we can obtain the same result by using the alternative method, z equal to x minus mu divided by the standard error. We plug in those same numbers, and this time we calculate 3.6. Now if we put in this second axis with the standard deviation, remember we're saying that our test statistic is plus and minus 1.96, and now we've calculated our sample mean to be 3.6 standard deviations from the mean, and 3.6 is greater than our test statistic of 1.96. So again, it's telling us that we reject the null hypothesis. Okay, so one more thing we can do here is to calculate the p-value. Now remember we said the p-value is going to be the area from our sample mean 118 to the right. So now we're going to calculate the area in here. That's easy to do now because we know that that's 3.6 standard deviations from the mu. So we're going to use our z table and calculate the area from 118 back. We'll subtract that from 0.5 to give us the area in the tail. So let's do that. Let's go to our z table. We'll scroll down to 3.6. The value we read is 0.4998. Okay, so 0.4998 is the area from 112 to 118. When we subtract that from 0.5, it gives us this tail area, p equal to 0.002. So that's telling us that we have 2 in 10,000 chances of getting that sample mean. Okay, so when we move that decimal point over, it's telling us that we have an extremely small probability of getting a sample mean of 118, and therefore that's what makes it significant. Because we said it's significant if it is 5 in 100 chances. And you see our chances of getting that sample mean are much, much smaller than 5 in 100. Okay, so the p-value of the observed level of significance is the probability of obtaining the sample result if the null hypothesis is true. So the p-value is used to measure the weight of the evidence against the null hypothesis. And in this case, it was very high, because it's telling us that we have a 0.0002 probability of getting that sample mean of 118. Sample results that are not likely if the null hypothesis is true have a low p-value and are evidence that the null hypothesis is not true. And that's what we just showed. Let's state it another way. What if our wording was, using the same example, that we want to test the hypothesis that the IQ is more than 112? Everything else is going to stay the same. Going to use the same population standard deviation, same sample size, same sample mean. But now we see more than. This indicates an inequality. Our mathematical relationship for more than is greater than. So therefore, our statement is the alternative hypothesis, mu greater than 112. And our null hypothesis then is the complement, mu less than or equal to 112. Our graph now looks different, remember, because now our significance level of 0.05 all falls in the right tail. And our do not reject area is everything to the left of that. So if we first calculate our critical value that defines that area, now we just have our hypothesized mu plus z times our standard error. And that calculates to be 114.75. Again, our 118 falls up in that right tail in the rejection region. The interpretation is we reject the null. However, our data supports that students have an IQ of more than 112 because our statement was actually that alternative hypothesis. So this is what I mean when we have to answer the question in two ways. One is we state it in terms of the null, and the second is we answer the question that was asked. So again, we are in the rejection region, so we reject the null, but our question was, students have an IQ of more than 112. And yes, we do indicate that our students have an IQ greater than 112. Again, the alternative method is just like we had done before, but now our test statistic was different. Remember, in our equation, we now used 1.65 because we have our z-value is different due to that area between our mean and 0.05 in the tail. So in here we have an area of 0.45. Let's look at one more worded problem. We could also ask that what if we state the student IQ scores are at least 112? This is a different question. So again, remember that words and the wording of problems are very important. Our values are going to stay the same, but now our hypothesis changes because we said we're stated that the IQs are at least 112. Well, at least the mathematical relationship is greater or equal. So now that's our null hypothesis, and the alternative is mu less than 112. This indicates that we're going to have a tail for the rejection region on the left. Now our statement is mu minus z times the standard error. And when we do that calculation, we see that our critical value is 109.25. Again, our sample mean falls in the do not reject area. So we say we do not reject the null, and our data supports that students' IQs are at least 112. You see that alternative method yields the same result in all three examples, but our test statistic has changed. So now our test statistic is a minus 1.65 since we're to the left of the mean, and our value 3.6 is greater than that, so therefore again we do not reject the mean. Let's look at one more example. Here we have Kohl's department store. They want to determine the amount spent per child in back-to-school spending. They hypothesize that $132 will be spent. The random sample of 25 orders, and they calculate the average spending to be $128 with a sample standard deviation equal to 3. We're going to test our hypothesis at alpha equal to 0.01. Now let's look at this a minute. We see that we have 25 orders. So n is equal to 25. Our sample mean is 128. We have a sample standard deviation equal to 3 and a significance value, alpha, of 0.01. We have no words in our problem that indicate an inequality, so we set our null hypothesis to mu equal to 132, the alternative mu not equal to 132. Again, we're going to do our diagram. The 132 is our hypothesized mean. Because it's an equality, we have two tails, and we split that significance 0.01 between those two tails. So we have 0.005 in each tail. Now, when we look at our numbers, we see we have a small sample size, n less than 30, and we have a sample standard deviation 3. That tells us we now need to use the t-statistic and not the z-statistic. So our equation is our hypothesized mu plus or minus t times s divided by the square root of n. Let's plug in our numbers and do our calculations. So our numbers, our values in dollars that define our do not reject region is 130.32 to 133.68. Now we look at our sample mean. Our sample mean is 128. Where does that fall? It falls in the rejection region. So our conclusion is that we reject the null hypothesis, and our evidence does not support the null that parents spend $132 per child. Now we need to go back and do one more thing here, because where did we get that t-value, 2.797? We see where we get all the other numbers in that equation. But remember, now we're using that t-table. And the t-table reads slightly differently. So let's review that one more time. So in our t-table, we're going to need to look for degrees of freedom. That's going to be n minus 1, 24. And then remember, our t-table reads the area that's in the tail, 0.005. Okay, so here we're going to go across the top and find the number 0.005, this column. And then we go down to 24. And we round up. So here we see that our number is going to be 2.79. So again, our evidence tells us that we do not support the null, and our sample mean falls in the rejection area.